My name is Timm Krueger. You can follow me on Twitter if you like. And I'm a researcher. I'm a Chancellor's Fellow working at the Institute for Materials and Processes, and I'm teaching in chemical engineering. What I want to talk about today is my research, which is, as some of you may recognize, blood flow, in particular the simulation of blood flow with application in disease diagnosis. And the first question I want to address is, what is the meaning of the saying, blood is thicker than water? You may know that. And actually it means, at least what we think nowadays what it means, that family is more important than friends. This is unfortunately not the original meaning of the saying, but I'm more interested in the physical content of the saying. Blood is thicker than water. What does it mean? It means that if you have blood and if you have water, then it is easier for you to pour water than blood, because blood is more viscous, as we would say, or in daily life, in daily language, we would say it's thicker. And the reason for that is that in blood, we have many, many cells, red blood cells, which are suspended in this liquid. And due to the presence of these cells, many, many cells, and you will see that, it is more difficult for blood to flow. And in order to illustrate this, let me give you an example. I think you know this guy, Dr. House. He's very intelligent, maybe a bit too arrogant, at least for my taste. And if you watch House on television or Netflix, then from time to time you see something like this, an illustration of blood flow, and you get the impression that blood is essentially water, and you find a few individual red blood cells inside. So you get the feeling it's very dilute suspension, but unfortunately this is not really correct, because blood looks more like this, right? Blood is a very dense suspension of red blood cells. This is a simulation of blood flow in a blood vessel with a diameter of about 100 micrometer or 0.1 millimeter. This is the size of one of your hairs. It is very small, but still you can see that you have a vast number of red blood cells flowing inside. And what I'm showing here actually is a subset of a blood vessel. You don't see the entire blood vessel, and that's the reason why you have cells appearing and disappearing here. It's just a simulation of a subset. But you may wonder now, what is actually the purpose of red blood cells? What do they do? And red blood cells, they're extremely important because they transport oxygen from your lungs to all your tissue in the body, right? Red blood cells are essentially containers which are filled with the liquid hemoglobin solution. And this hemoglobin can take oxygen, and the oxygen is flowing inside of the red blood cells through your body to all parts of your body, to all your tissue. And you can imagine already that if you have this dense suspension of blood, due to all these particles inside, it is flowing more slowly, and that's the reason why blood is actually thicker than water. Blood is a remarkable fluid. As I said, you have red blood cells inside. Red blood cells transport oxygen, but you also have white blood cells, like this one. White blood cells are part of your immune system. Whenever you have a disease, a bacterial infection, for example, white blood cells are chasing bacteria or viruses. There are also platelets, blood platelets, and they are responsible for blood clotting. If you have an injury, and I think it happened to everybody, you cut yourself or something happens, you're bleeding, your blood vessel has to heal itself. And the first step is blood clotting, where the bleeding stops. And afterwards, your blood vessel can actually be healed. And the platelets, these tiny guys here, they are part of this clotting process. Blood is actually a very important fluid, a very important liquid, and it is a mirror for your own health and disease state. Imagine you are sick, you're feeling very, very sick, and you go to the doctors. What do they do quite often? They take a blood sample, right? They take a blood sample, and after a few days they get back to you and say, everything is fine, or maybe they say you have too many leukocytes, which means too many white blood cells, which is an indicator for some kind of infection, for example. Or if you're feeling very tired and they say the number of red blood cells is reduced for some reason, That's actually the explanation why you can feel tired, because you have less oxygen circulating in your body. And blood is very important because, first of all, it delivers all the nutrients in your body, but from a diagnostic point of view, if you take a small sample of blood, you can find out quite a lot about the disease state of a patient. Another example are circulating tumor cells. If there is some kind of cancer in the body, sometimes you find individual tumor cells which are circulating in the blood flow. And this is extremely important to know because these cells can lead to metastasis, which is of course very dangerous. And if we find a way somehow to detect these circulating tumor cells in blood, this would help us quite a lot in diagnosing and treating cancer. Right. So blood is truly a very important fluid. But now you may ask me, okay, we know that blood carries a lot of information about the disease state, but how do we know that? How do we analyze blood? Nowadays, what happens typically is there's a blood sample, it is sent to a lab. The lab is a big room filled with expensive equipment. You have many, many chemicals. You have highly trained people working there. And it takes several days to have the results if it's more than just a simple blood test. So for example, if they are looking for specific diseases, it can take several days or even weeks. These devices here, this is a centrifuge. They can be very big, they can be very expensive, they are noisy, they consume a lot of energy, right? And if you think about this, you can do so many things in a lab nowadays, but this reminds me of a big computer you had about half a century ago. 50 years ago, computers were enormous machines, like a lab nowadays. You have a machine filling a room, very expensive, very slow. Computations were very slow 50, 60 years ago. But nowadays, if you take a look here at integrated electronics, you would agree that nowadays computations are much, much faster. Computer chips are much, much cheaper. They are extremely small. You have a computer chip in every mobile phone, which is more powerful than what you had 50 years ago in these machines which were room-filling, right? And now the question is it somehow possible to develop something similar for the lab? Can we have something which is called lab in a chip? And the idea here is that we have a device which is maybe as tall as your fingernail. It consists of a complex network of tubes and channels which are very small, maybe the diameter of one of your hairs or even smaller. You can inject certain fluids like a blood sample, and this device, much, much smaller than a huge lab, can give you, after a few seconds or minutes, a result and tell you, okay, there's some kind of disease or something is wrong with you, something, right? So in principle, the big challenge we have nowadays is to develop something which is akin to integrated electronics for biological fluids, essentially. And here the question is how we can do that. So if you think of an engineer, what does an engineer do typically? We think that engineers put things together, make things work, right? This is what engineers do typically. But there are also other engineers. Take a look at these kids here. What do you think they're up to? They have a television and they have screwdrivers. Is it a good sign? Something will happen on this television, right, in the next, say, 15, 20 minutes. And if those were your children, would you be upset or would you be proud? I think you should be proud because these children are young engineers who want to understand how the television works. They want to take it apart, they want to see what's inside, and they want to investigate how things work together, right? And this is exactly what we have to do with blood in order to find out what's happening. We have to take it apart, we have to understand what's inside, and we have to develop new methods to analyze what diseases, for example, affect in your blood, and how we can diagnose these diseases. What you see now is a simulation of one of my PhD students, a computer simulation. You see 3 different types of blood cells. The white blood cells I talked about, part of the immune system. Red blood cells carrying oxygen. And platelets, the tiny guys here, These cells are moving in a complex geometry. You see this pattern of obstacles, of pillars in green. And if you look carefully, you see that at the end of the simulation, all these particles reach different regions of the device. The white blood cells are in outlet 3, red blood cells are in outlet 2, and the platelets are in outlet 1. But in the beginning of the simulation, all the particles were mixed together. In other words, this device here, which would be in reality relatively small, because the cells are very small, it's maybe a few millimeters, a few centimeters large, it would be able to separate blood components by size or by shape or whatever. And this is exactly what we want to achieve, because if there are circulating tumor cells, we want to isolate them in order to find them. Right? We have to find them somehow, because there are only a few of them in a quite big volume of blood. So maybe you have 1 million red blood cells and only one circulating tumor cell. How do you separate these cells? Now, the question is, why do we need simulations for that? And this is really the question I want to answer. Why do we need computer simulations to study how we can separate blood components, blood cells? And the answer is already here, because take a look at this geometry here. You see these triangular shapes. What happens, for example, if you change the shape of these posts? For example, if you make them circular or like a square, or you rotate them, you make them bigger, you make them smaller, you change the spacing between them or their relative alignment. All these ingredients have a very important effect on how reliably this device works. And if you now perform experiments, you can actually build these devices in reality. It is possible, people do that all the time. But it takes a lot of time to design such a geometry and to run experiments. And imagine after 1 week, after 2 weeks, you get results, and these results are negative. So basically it doesn't work. Do you learn something? That's the next question. Can you actually learn from the errors you do in experiments? And this is often quite complicated in these systems, because you have not really a good idea why it hasn't worked properly. So you're stuck. You don't know what to change next in order to improve your design. And simulations can help here, because in simulations we can very easily change these parameters individually, rerun simulations, and see what happens to all these particles. It is quite simple for us to see what happens if we replace this triangular shape by, for example, a circular shape. And what I want to say here is that simulations can help to accelerate the experimental process, because we can provide additional insight which cannot be gained experimentally, and we can collaborate with experimentalists and give them some advice in which direction they should change their device parameters. The biggest challenge we have here is actually validation. How do we know that the simulations are reliable? Everybody can write some kind of code, computer code, and can run a simulation. That's fine. But how do we know that the simulation actually makes sense? Right? This is the biggest challenge we have. We cannot just run simulations like this and say, oh, we found something interesting. We have to validate our results and our simulation code. And also here it is extremely important to work together with experimentalists, because we can, for example, simulate systems they can measure experimentally and the other way around. So I hope that I convinced you that, first of all, you shouldn't believe everything you see on television, which means blood flow doesn't look like this, it looks more like this. And the other takeaway message for you today is computer simulations are extremely important if you want to develop the next generation devices for disease diagnosis based on blood analysis. Thank you very much for coming here. Thank you very much for your interest.
This production is brought to you by the University of Edinburgh.